Hello, Coach Travis here with another calculus video. So here's our problem. We got a population of fruit flies, and that population is increasing at this rate, this number of flies per day. Okay, so I guess as the number of days changes, the population is changing more rapidly. It's growing exponentially. And okay, the population starts at 200 flies. How many flies are added to the population between days 3 and 13? Okay, so what's going on here is this is asking us to predict the net change in the population. We want to find the total change in the population between day 3 and 13. So that's known as a net change. But the problem is we don't have the formula for the population. They're asking us for, so how many more flies do we have on day 13 than we have on day 3? But we don't know. We don't know how many flies we had on day 3. And we don't know how many flies we have on day 13. So how are we supposed to answer this? All we know is the rate at which the flies are changing. We know the rate at which the population is changing. So this is one of those problems where you have to take a rate and turn it into a total change. And whenever that happens, you should think that is a job for what we call the net change theorem. So the net change theorem says that if you know a derivative, and derivative is just our shorthand word for rate of change. So if you know the rate of change of some function, so lowercase f is the rate of change, uppercase F is the original. So if you know the rate of change, then if you integrate the rate of change over the interval, then you get the net change. So the way I think about it is, since the definite integral is also the area, the way I think about it is the area under the rate of change graph, that's this, is equal to the net change. And that's this, of the original function. So little f was the rate of change, big F was the original function. So it's a way of relating how fast something is changing to what's the total change in the actual something. So essentially, this is what calculus allows us to do. The calculus allows us to, if we know how fast something's changing, then we can actually find out how the total quantity, the net quantity that the something has changed by. And that's actually a really big deal. So all right, so how are we going to do this? Okay, well, again, what did the net change theorem say? Okay, so it said if we integrate the rate of change, then we get the net change. And so, okay, so for us, the rate of change was the function that we were given. So we were given, we said, oh yeah, this is the rate of change right here. So, all right, so the change in our fruit fly population is going to be the integral of the rate of change. And the rate of change function is 4 times e to the 0.02 times t. And I'm integrating with respect to t. And then the integral, the limits of integration need to be the change in the time. So the time changed from 3 to 13. So that's what we need. And you might be wondering, wait, what about the 200? So actually, I think the 200 is a red herring. I don't think we're ever going to need that, because if you think about what the net change theorem says, the net change theorem says all you need to know is the rate of change and, what's your time interval. The rate of change theorem, or sorry, the net change theorem doesn't say you have to know the initial population. So the way we're doing this problem, I don't even think we're going to need that 200. Now there are other ways to solve this problem. Some of you might think of a way to do this problem in a different way, and that different way would actually use the 200. So there are other ways to do this problem that might use the 200, but I think we can actually answer this question without even knowing that 200. And that's actually pretty cool, because again, yeah, like if the problem hadn't even told us that, we would still be able to answer this question. You might say, oh, there's not enough information, but I think there is. Okay, well anyway, let's get rid of that. All right. So I have to evaluate this definite integral now. Okay, well, so this is kind of a complicated function here. When I look at this, it looks kind of like I see an inside and an outside function. Like I see that there's sort of an inside function of 0.02 times t. And whenever I see something like that in my integral, I think, oh, that's a job for u substitution. So I'm going to take that 0.02t and I'm going to replace it by the letter u. So my integral is going to become the integral from 3 to 13 of 4 times e to the u. And so let me change colors. So there's a u. So that complicated thing now is just the nice letter u. Okay, but now this is a problem because I have u's and t's mixed together. I do not like to have integrals that have multiple variables in them. So we need to figure out, basically we're making a commitment to u now. T is what we started with, but we couldn't do the problem with t's. So now we're making a commitment. We want to get rid of all the t's and replace them with u's. But we have to do that in a mathematically correct fashion. So you can't, what I mean by that is you can't just cross out this t and write a u there, because that's cheating, and that it's not true. dt is not the same as du, as we're about to see. So over here on the side, what we'll do is we'll find the derivative of both sides of this equation with respect to t. So the derivative of u with respect to t is just du dt. And then the derivative of 0.02t with respect to t is just 0.02 and no t. And now I can multiply both sides by dt. So I get du is equal to 0.02t. What am I doing? No, not t, dt. It's dt. And then now I want to solve for dt, so I could divide both sides by 0.02. So I have 1 over 0.02 du is equal to dt. And now I bet we could simplify this. Like, do you happen to know off the top of your head what's 1 divided by 0.02? And if you think about it, well, like I think about this as 2 cents, and this is $1, and 2 cents goes into $1 like 50 times. So this is 50 du is equal to dt. All right, awesome. So I can come back over here to my integral, and I can say this is going to be the integral of 4 times e to the u. Oops. 4 times e to the u. And now instead of dt, I can write a 50 and a du, because dt is exactly equal to 50 times du. Okay, and now you might be saying, wait, Travis, you forgot something. You forgot the 3 and the 13. But I'm actually going to say, well, I actually forgot those on purpose. And I'm going to put question marks there. Because the idea there is that the 3 and the 13, those are how many days have gone by. Those are t values. T is equal to 3, and t is equal to 13. But we're now living in the u world. And so the limits of integration, t is history. We've gotten rid of t. And so the 3 and the 13, those are going to be history also. So you should not put a 3 and a 13 here, because 3 and 13 are the limits for t. But we're now integrating with respect to u. So you could take the time to figure out what should go here. But my preferred way to do these problems is just not to worry about it and just back substitute at the end. Get t back when we get done, bring t back at the end, and then we can bring back the 3 and the 13. So you'll see what I mean when I get there. But for the moment, I'm just not going to worry about what those things are. So, okay, so now this integral is now going to be the integral, wait. Actually, let me simplify it a little bit. So 4 times 50 makes 100. No, it doesn't. It makes 200. Just checking. It makes 200, and then we're going to have the integral. I can factor constants out of my integral. And then I just have e to the u du. All right, and now this is one of my favorite we know that we now integrate, we have e to the u, and we're integrating with respect to u. And so now I can use the fundamental theorem of calculus, and I can say, okay, that the fundamental theorem of calculus says that this definite integral is going to be the antiderivative of e to the u evaluated at the two limits. So using the fundamental theorem of calculus here, I need to figure out what the antiderivative of e to the u with respect to u is. But that's an easy one, because e to the u or e to the x, or however you want to call it, is the best function in calculus. It is its own derivative. And if it's its own derivative, that also means it's its own antiderivative. So actually nothing happens here. To the antiderivative of e to the u with respect to u is just e to the u. Okay, so that's the antiderivative part. And now I can't continue until I know what these question marks are. And I decided I didn't want to know what those question marks were, because I promised you what we could do is we could just back substitute. So what I can do here is I can say, oh, well, that u, we said u was the same thing as 0.02t. So, all right, so this, I can replace the u by 0.02 times t. And now that I have the t's back, then the 3 and the 13 can come back as well. I've left the world of u's, and I'm now back in the world of t's. Okay, and now we're pretty much done. Now we just have to plug in the numbers. So this is going to be, so now I take the 200. It just stays there. And okay, so the first thing I do is I plug in the 13. So that's going to give me e, so let's see, 13 times 0.2 is 0.26. And then I have to subtract what I get when I put 3 in for t. And so that'll be e to the 0.06. And that is the final answer. Oops, wrong tool. that is the total change in fruit flies. So the total change in fruit flies from day 13 from day 3 to day 13 is whatever this number is right here. Oh, and I guess it says it wants you to round your answer to the nearest whole number. So you go at this point, you get out a calculator and you figure out what this is. Oh, interesting. When I look at this, you see that the number 200 came up, and that was also this 200 that we referred to here. But that's just a coincidence. That is just a coincidence because, that 200 came from 4 times 50, and the 4 came from, that was the velocity, and the velocity doesn't have much to do with the initial population. So that don't try to read anything into that. The fact that this was a 200 and this was a 200, that's a complete coincidence.